Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 44. So in the last lecture, we had looked at the connections between the various Einstein coefficients, which were called as B12, B21 and A21. So these corresponds to emission, and this corresponds to absorption, right? And this corresponds to spontaneous emission, and this term corresponds to stimulated emission, correct? So we saw that all of these three terms, right? The connection between all these three was important because once we find one of them, for example, either B12 or B21, right? That could be obtained from quantum mechanics. And by obtaining this, we could connect it with the intensity of a spectral line. We stopped the lecture with seeing the connection between these three, and I said that this could eventually be connected with the intensity of a spectral line, right? And from which, we get information about whatever molecules or atoms could be present in space. So that is our objective behind studying all this. So in this lecture, right? So this was just a small recap. Now in the present lecture, that is lecture 44, we shall be looking more into the various aspects concerned with the intensity of a spectral line. Okay. Now, before we proceed further, recall that we had a brief introduction into quantum mechanics, right? I had taught you about how we get what is called as the time independent Schrodinger equation, and that it is extremely relevant to describe the molecules that are obtained in space, right? You remember that, right? Now we shall see one more application of quantum mechanics in this lecture concerning the intensity. However, you may be thankful that there is actually not much of a derivation. I will give you the final results from quantum mechanics. How shall we do this? Now, consider this triple integral. Consider this triple integral. I'm going to label this like mu fi is equal to this triple integral, right? Something like psi star, right? Psi star I, and I'm going to call this mu with a hat, and I'm going to call this psi f dx dy dz, and the limits of all these integrals are from minus infinity to plus infinity, minus infinity to plus infinity, and minus infinity to plus infinity. Now you might be wondering, what did I say we shall be discussing in this course? Something about intensity. Now what does that have to do with some random expression, right? A scary looking expression, especially concerning some triple integral and all that. Okay, right? I will explain the connection to you. Now, and also I also brought in quantum mechanics, right? So where is quantum mechanics also coming here? Well, you see psi, so therefore there should be some connection somewhere between quantum mechanics. Are we good? Right? Yeah. So let us see what this expression means and how this is connecting quantum mechanics with the intensity of a spectral line. All right. First things first, note this. I gave this expression to you. Let's call this this expression as expression I, because this is going to be connected with the intensity of a spectral line. And note that I did not derive this. Okay, please be clear about this. Can this be, using the ideas of quantum mechanics, we can get to this expression, okay, right? So I did not derive this. I did not also tell you, I did not also tell you how this is obtained. I'm just giving you some expression, okay, right? And now I'm going to tell you the big thing about this expression. This expression, right? This expression I, right? I'm going to tell you that this expression I is extremely important. It is, in fact, is the fundamental equation fundamental expression in spectroscopy. Okay, so this is the fundamental expression in spectroscopy, and it is on the basis of this expression, that we can determine how feeble or how strong, lines may be obtained in any spectrum. Okay, right? So this term over here, right? The term on the LHS of expression I, your mu Fi, right? Okay, right? That is actually called as the transition moment. Okay, your mu Fi is called as transition moment. Have you seen the symbol mu in this course before? Have you ever seen it? Well, we did, right? Briefly in a tutorial while we were discussing the idea of dipole moment, right? So this transition moment, which is called as mu Fi, right? Where F refers to some final state and I refers to some initial state. We are typically talking about, some transition happening from either a lower energy state to an upper energy state or vice versa. In any case, right, F refers to a final state and I to an initial state. Okay, right? So this is what is called as a transition moment. Okay, right? The magnitude of the transition moment, right, is a measure of how intense the spectral signal will be. Okay, so what I've written here is the magnitude of this particular term right here, right? That is going to be a measure of how intense the spectral signal will be. Okay, so again, I know that I'm not telling you how this expression came about because that is going to take a lot of time. It is for a more specialized course in spectroscopy or applications of quantum mechanics. But this being astrochemistry, I'm just going to give you this expression. Okay, so this is the LHS, and of course, as I've always told you in this class, even if I have not derived any expression, I'm very clearly telling you that this can be derived, but we're not deriving it for the sake of time. Yet we still need to understand all the terms, right? So we've understood what the LHS means. It is called as a transition moment, and its magnitude is a measure of how intense the spectral signal is going to be. Okay, now I'll delete this page. So now in expression I, we're going to be looking at what all the terms in the RHS mean. Now, in the RHS of expression I, right? I'm talking about over here, right? Now, I'll start with dx dy dz, right? Dx dy dz are nothing but small length elements along x, y, and z directions, right? And overall, we get the volume element once you multiply all these three. Okay, and accordingly, the limits, right? The limits are going to be it's a triple integral. So you go from dz dy dx, right? So then the triple integral, the limits I'm just going to include all space encompassed by this volume element. All right. So that is the meaning of these limits. So limits, right, to enclose the complete volume element. Okay, right? So what have we understood? We have understood the dx dy dz and the limits of the integrals. Okay. The next thing is, I'll delete this page. The next thing is, what are these wave functions? Psi, right? So psi I and psi f are the, okay, I'm not going to use any technical jargon. Strictly speaking, they're called as the electronic wave functions. Okay. But I'm not going to go to the quantum mechanics of this part at all. I'll just say they are the wave functions of the molecule, right? Initially and after the electron transition. Again, so I say wave function, right? Have we seen the word wave function before in this course? We did, right? When we kind of obtained h psi equals z psi, and we saw the free electron, and then the electron whose motion was restricted to move along the x direction between say x equal to 0 and x equal to L, right? During those occasions, we saw this word wave function, right? And I've told you that this is purely mathematical. I insist again, this is purely mathematical. The wave function is not obtained as a result of any experiment. Okay, so we get this wave function mathematically. Okay, right? And this is the any molecule, right? Any molecule could be mathematically described using a wave function, right? Strictly speaking, this is called as the electronic wave function. Okay, but don't worry about the jargon. I'm just telling you so that you know, like if you were to read more on this topic, right? Especially if you are understood in the if you want to understand the complete derivation of this of the terms, right, and how we exactly get this expression, then it might be of help to you to understand that this is an electronic wave function that I'm talking about. Okay, for the purpose of our discussion in this course, it is just some wave function. Okay, so psi and psi f are some wave function, right? And before and after the electron transition. Okay, right? And notice that my wave function is a function of all the three variables x, y, and z, because we are living in a three-dimensional world, right? So any molecule is also going to be described in 3 dimensions. All right. So this is psi of x, y, z. Recall when we were discussing, you know, the electron electron whose motion was restricted. When we were discussing that problem, we only had a 1-dimensional wave function. Now we have a 3-dimensional wave function. Okay, right? Now notice it. Also, just a small note before I proceed further. I'll make it a small digression. Okay, to explain further about this particular thing, wave function. Okay, see, now while we were talking about the wave function of an electron with restricted motion, we saw that the number n, right? The number n was used to describe the energy, right? For an electron, an electron whose motion was restricted. I may be writing in small letters. So this is electron whose motion was restricted. We saw that the wave function was given of the form phi equals something like a sine nx, right? We got this, right? Yeah, n pi x by L to be, including all terms also, n pi x by L, where n is an integer, right? It could have all this. Now this word, this particular term n, we just saw it as an integer, right? Now this n is more technically described as a quantum number. So the n over here, right? the derivation continues. So I will just keep this part intact. So the n is also called as a quantum number. Okay, so the n is called as a quantum number. So quantum numbers are typically, like integers. For the most part, they are either integers or in some cases, right, they can also be real numbers. Okay, but they are not irrational. Okay, they are rational numbers always. So n is either an integer or a real number. Okay, so n is what is called as a quantum number. Now for this particular problem, this one-dimensional problem, we got one quantum number. Okay, but for a real electron, okay, right, for a real electron, each wave function, okay, right, each wave function, this is especially called as the spatial wave function. Okay, right, your psi of xyz. So this is the end of the derivation. Okay, I just wanted you to be introduced to the idea of a quantum number, right? So this quantum number comes about from the problem of, in this class, we saw that the concept of quantum number arises due to the boundary conditions imposed. Okay, similarly, for any bound wave function, see these molecules, right, these are also going to be bound systems. Now bound in what sense? Bound in the sense that the electrons in the molecule are going to be attracted to the nuclei in the molecule. Okay, overall. Okay, right? So these molecules are what are called as bound systems. So similar to, like the quantum numbers arising in these bound systems, right? Here also, for this wave function also, right? Each of these wave function is attached with a set of quantum numbers. Okay, for molecules, typically, you have like 4 quantum numbers. Okay, right? If you consider only the spatial part, there are only 3, but including what is called as a spin part, okay, right? There will be 4. Now, for this particular wave function, okay, for this particular wave function, when I'm considering only the spatial part, there's going to be 3 quantum numbers plus one more, so it's actually 4, right? And 3 from this specific wave function we use here. All right. I'm very certain that, I must have been reasonably confusing. Okay. So I will clarify further again. I'll write all of this neatly in this board. Okay. All I was telling so far is that given a psi of xyz, right, we associated with 3 quantum numbers. All right. Just for example, right, if you consider the hydrogen atom, you have been studying in your 11th and 12th standards onward, right, that there are 3 quantum numbers associated with that. The principal, which is the n, and then I think the next one is called azimuthal, which is the L, and then the magnetic quantum number, which is the m sub L, right? They are associated with the spatial part. Then there is one more part which is called as the spin quantum number. Okay, 3 quantum numbers as part of it, as part of psi of xyz plus 1, right, which is called as the spin quantum number. Okay, right? Now, of course, the total number of quantum numbers is going to be 4, but from this wave function itself, from this wave function, which only contains the spatial part, there are going to be only 3 quantum numbers associated. Okay, so now, based on, like all these 4 quantum numbers, okay, just we can obtain, okay, right, we can obtain information about how intense the signal is going to be. That is why I spent some time describing, qualitatively how the notion of quantum numbers arise from wave functions. Okay, right? So each wave function is associated with some quantum numbers. Please note this. All right, please note this, and we shall continue our discourse as to how all of this is overall, right, connected with the intensities very, very soon. Okay. So what did I tell you so far? We are basically looking into all the terms in the right hand side. We saw what dx, dy, dz were. We also explained what the limits were. I told you what the wave functions mean, right? I told you what the wave functions mean, and I told you that the wave function could be associated with quantum numbers. Okay, the specific form of psi itself is associated with 3 quantum numbers, right, as part of the psi of xyz itself, plus one more quantum number called a spin quantum number, which cannot be visualized. Okay, cannot be visualized. Note this point also. So the spin part alone, right, it cannot be visualized. Whereas, like the quantum numbers corresponding to these three, right, we can kind of visualize. That is, we can plot functions and all this. But the spin quantum number can't be visualized. Okay, right? Please note this. When I say it can't be visualized, it arises completely due to quantum mechanics, and we'll have trouble, to visualize the spin part. Okay, all right. So one more detail about the wave function is that, okay, now see, so here I've put a star here, right? So in this term, corresponding to psi f, there is no star, but here there is a star. What does it mean? It means that I take a complex conjugation, okay, right? For example, let us say that my psi is equal to e to the power ik f of x, y, z, some function there, okay. Now my psi star, where I here is the square root of -1, okay. Now this I is an index, okay. This I is an index to say initial, right? And this I refers to I, which is the conventionally used symbol to denote the square root of -1, okay, the imaginary number. All right. So therefore, by putting a star, I'm taking a complex conjugate. So this becomes e to the power minus ik f of x, y, z. Well, if I assume that my f is just some real valued function, it will be a real valued function here also, and will not be affected at all. So just the I becomes minus I. Okay. So now this is what is meant by taking a star. All right. Now what is the only thing that is left unexplained in this whole expression I? Well, it is this term mu, right? A mu also with a hat, right? So what is that term? So the only term missing here is mu with a hat is nothing but what is called as the dipole moment operator, right? And that is defined, right, as, okay, right, by this expression, where we know Qi is the charge on the ith atom, and Rij just the modulus of Rij, it just refers to the distance between ith atom and its neighbor. Okay, see, this is one way to describe the dipole moment operator. There are other ways also. For our purpose, this suffices. Okay, right? So recall, what did we see? Dipole moment is nothing but charge times distance, right? We, I think, saw in a tutorial earlier, and we also discussed that the dipole moments are measured in dBys, which is a very small value if we convert to SI units, right? Something like 10 to the power minus 30 coulomb meter or something. Recall? Yeah. All right. So effectively, it is a charge time distance thing. Okay. So overall, right? So overall, this expression here, right, gives you what is called as the transition moment. And by calculating this, okay, right, by calculating this, you can obtain the wave function mathematically. You can use your dipole moment operator, and after the operation of the dipole moment on the final wave function, you get one more function, and this is one more mathematical function, and then you carry out this integration. Okay, right? You can do this. You can do this by many means. Either analytically, that is like if you know the formulae, or like you can also do it numerically if you don't know the formulae. There are several approximations involved. Okay, let's not worry about how exactly this is evaluated, but nonetheless, you can ultimately get this integral. Okay, and the larger the magnitude of this mu fi, okay, right? The larger the magnitude of this mu fi, right? Larger phi, more intense. I think I've already told this. I'm repeating it for emphasis. Okay, more intense the spectral line. Now, and there are sometimes, due to the symmetry of these wave functions, okay, right? Sometimes your mu fi your mod mu Fy can actually be 0 too. Okay, right? So when your mu Fy is actually 0, what it means is that, what would be your guess? Well, your guess, a very intuitive guess based on our discussion would be that, okay, the more intense this is, so therefore at 0, the intensity should be 0. Okay, it's not actually 0. It just turns out that your mu Fy, when the mod mu Fy is actually 0, intensity is very low. Not 0 though, not this point. Okay, intensity is very, very low. So I've written it in the downmost portion of the board. So maybe it is not clear. What I've written is the modulus of mu Fy can be 0 too, and in those cases the intensity is very, very low. Okay, right? It is not 0 because there may be. I'm not going into more details, but it is not exactly 0. That suffices for our astrochemistry purpose. Okay. Now these points, okay, right? These 2 points are of tremendous value in spectroscopy, which is the technique used to detect molecules in space. Okay, right? So now that I've explained everything in this expression, I'm going to delete this. Based on these 2 aspects, right? Based on these 2 aspects, the evaluation of your mu Fy, okay, right, which can be connected with intensity, leads to what are called as selection rules. Okay, please understand this. Okay, right? What are called as selection rules, and those selection rules will be expressed in terms of the quantum numbers. Now, do you see, why I was painstakingly taking the effort to explain to you, what all these quantum numbers, how all these quantum numbers could arise from the wave functions, right? You may at that moment be thinking, oh, this is probably unconnected. Why do we bother? Well, we bother because the evaluation of mu Fy, right, will give us some ultimately it's an evaluation, right, which leads us, it's an integral, and calculating it is going to lead us to some sort of a function, right? Now that can be expressed in terms of the quantum numbers, and so the selection rules, right, will be in terms of quantum numbers. Okay, right? So the selection rules. But what are the selection rules? Well, and how are the selection rules connected with the intensity? Those are the things, we shall be addressing in the next class. Okay, for now, I'll just summarize what we saw in today's class. In today's class, we started looking at what is called as the transition moment integral. Okay, right? The expression I. Okay, now we were just, enunciating, and I was explaining to you what all the terms in that expression meant. So there was a volume element and there is a triple integral. The limits are chosen to enclose all volume, right? And we have 2 wave functions. One wave function corresponding to the initial state before electronic excitation or before electronic de-excitation, right? It's just the initial state. It could be lower or upper state. And we have one more wave function corresponding to the final state. And then each of these wave functions could be associated with some quantum numbers, 3 quantum numbers as part of psi of xyz itself, which arise from the spatial part of the wave function, and one more, which is a spin quantum number. Okay, right? And we also saw that in the integral, there was a psi star, that is like taking a complex conjugation. We saw what taking a complex conjugation meant in our context. Okay, and by evaluating this integral overall, we could correlate with the intensity of the spectral line. Larger the magnitude of this mu Fy, the spectral line is more intense. Lesser it is, if it is lesser it is less intense. If it is 0 exactly, then the intensity is very, very low. Okay, it is not, the intensity itself is not 0. Please note this point very carefully. It's a point of astrochemical relevance. And lastly, we said that the evaluation of this integral also leads us to what are called as selection rules, right? Selection rules, wherein, the selection rules can be expressed in terms of the quantum numbers. How exactly, I have not told you. And How the selection rules will be connected to intensity, we will discuss in the next lecture. Thank you so much.